So in this video, I go over the derivative of inverse functions. So let's start by reviewing some facts about inverse functions. So we say that two functions f and g are inverses if their composition in either order reduces the identity function, which means specifically on an algebraic level that f composed with g at x is the same as just x for all x in the domain of g, and g composed with f applied at x is just x for all values in the domain of f. Notice that the two identities here I'm mentioning over different sets. That's one of the reasons that inverses are actually kind of difficult for most students. Now, just to give you an example, these two functions here I claim are inverses. To show that, I'll only verify one of the identities. Technically, I have to verify both, but I'll verify only one of the identities. Let's go ahead and look at that composition. So I want to know what g composed with f of x is. It's equal to this expression. But then the square root of the square doesn't cancel. It gives you the absolute value. But since the domain is restricted to only those values that are the domain of f first, the domain of f is all x greater than or equal to 3. So then x minus 3 is already non-negative. So the absolute value is not needed, reducing the result in the end to just x. So that shows that g composed with f of x is just x, verifying 1/2 of the definition. You should also notice that just the definition of the inverses implies this, that if f of a is b, then g of b is a. In other words, the input of one function becomes the output of the other. Let's look at these two functions a little bit more closely. If you graph them, they look like this. So then the one curving upwards, that's the parabola, half of it, that's f. And the one that goes this way, that's the square root function. That'd be the g of x function. I'd like to know how their domain ranges compare. Well, but I just said moments ago that the input of one function becomes the output of the other. So using that, we can easily find the range of g because that has to be the domain of f. And the domain of f is all numbers bigger than or equal to 3. I can easily find the domain of g because I know the range of f, and that would be all numbers bigger than or equal to 0. Notice that I can find that. I can get those answers without even looking at the function g because I know the domain and range of f. Now there's something else you can get. There's another relationship between these two graphs. The current graph has been stretched in this direction because the pixels actually are a little longer this way than they are tall. So the graph naturally stretches in one direction if you go -10 to 10 in both directions. So you can compensate that by using different zoom settings. Doing that zoom setting for this calculator, I wind up getting that graph. Now, if you look at the point a comma b on one graph, the corresponding point on the other graph must be b comma a because the input and output swap. So it has to look like that. Now, if you draw on the line y equals x, you certainly should be able to see that those 2 points are reflections in that line. It's not even hard to prove. It's not even that hard to prove actually, but it's not something I care about right now. So the graph and its inverse are supposed to be reflections in the line y equals x. So let's go ahead and find how the derivative of f and the derivative of g relate to each other, using corresponding inputs for each, of course. I mean by that is that the point a comma b, if it's on the graph of f, then the corresponding point would be b comma a on the graph of g. So for example, if you take f of 5, you can evaluate to get 4, but that means 5 comma 4 is on the graph of f. That means 4 comma 5 is on the graph of g, so g of 4 better be 5. Let's find the derivative of f at 5, and let's find the derivative of g at 4 and see how those numbers compare. Well, we can easily compute the derivatives because I gave you the function. So there they are, those are the derivatives. And then I just plug in 5 and 4. So the derivative of f at 5 gives you 4, and the derivative of g at 4 gives you 1/4. The interesting thing is to notice that they're reciprocals. Now you wonder, is that always true? And yeah, it's not even that hard to see why it should be. The proof, of course, is more challenging, but to see why it should happen is not that hard to see. Look at the tangent line to the graph of f at the point 5 comma 4. Notice there is a corresponding change in x and y. Think of those as numbers. There's a certain change of x, a certain change in y, and the slope is the change in y over the change of x. But then, when you go and find the graph of the inverse, everything swaps. So that means then, when you look at the tangent line for the graph of g at the point 4, 5, the old change of x becomes the new change of y and vice versa. But the ratio is still change of y over change of x. So all that happens is in that ratio, the numbers swap places. You get reciprocals. So we should find that the derivative of the inverse is found by taking the derivative of the function and just reciprocating that number. All right, so then I've implied the derivative rule for inverses. It is one of those rules, though, that you will really not get to use very often yourself. Instead, we'll derive new rules from this one. Those are the ones you'll memorize. To warn you, though, you will see this again. You'll see it again probably in Calc 3 at least once, and I believe you see it a couple times after that in differential equations. But even then, you don't actually yourself use it. Your teacher will use it for you. So the theorem's really, really neat because not only does it tell you how to find the derivative of the inverse, it also goes and tells you that there is an inverse in the first place. So the assumptions are, assume that you have a function f that is differentiable on some kind of open interval. That means the derivative exists that entire time. But also the derivative is non-zero on that interval. Then you get 3 nice results. The first one is the function has an inverse. That's neat, because that means now we have a quick way to find out if a function has an inverse. We just go and take its derivative and show it's not zero. The second thing is, not only does the function have an inverse, but that inverse is differentiable on the range of the function over that interval. And third, not only is it differentiable, I can tell you how to find the derivative at different values of the input. The value of the derivative at a point B in the domain of the inverse just equals the reciprocal of the value of the derivative of f at the corresponding input, which in this case would be a, or the inverse of b. In notation, you get that awful looking rule. That's the thing we'll use by far the most in today for the rest of this particular video. But there are alternate ways which are faster to write. So you also have this way here using more like Leibniz notation. And if you just get rid of the evaluation, just get rid of all the evaluations and think of it as functions of x, functions of inputs, and you say that y is a function of x, that means x is a function of y. That function is called the inverse function. So the derivative of x, the inverse function, in terms of its input, y, so dx over dy, has to equal 1 over the derivative of the original function, which would be the derivative of y in terms of x. Notice in Leibniz notation, it says that the dy dx can be flipped, and it seems to be okay. This is only true, though, if the function is invertible in the first place. Well, now that rule looked pretty complicated, so let's do an example. I'll use a function, f of x equals x squared, because its inverse is already known. That way we can find the derivative 2 ways. One, the normal way, and the other, the new way I just showed you. So I'd like to know then what's the derivative of this inverse function. So I know that since the derivative of the function f is 2x, then with the rule I gave you, the derivative of the inverse is equal to 1 over the derivative of the function evaluated at the inverse. Well, but I know the inverse function, it's just the square root of x, so I can replace it with what it's equivalent to. So I have 1 over the derivative of the function evaluated with the square root of x. But the derivative of the function is just 2 times the input. So that gives you 1 over 2 times the square root of x. That should be the derivative of the square root of x. Now, if you do it the old way, to find the derivative of the inverse, you just write the derivative of x to the 1/2. That brings the power down, keep the base, reduce the power by 1, and that is 1 over 2 times the square root of x. So it seems then that this provides evidence that the theorem I gave you is true. I'm just not trying to prove it in general right now. Let's do another example, but this time let's go and do a problem where I don't find the equation for the inverse first, and I'll still be able to find its derivative. So I'd like to know if f of x equals x cubed minus 5, what is the value of the derivative of the inverse of that function where x is 3? Now, if the input for the inverse is 3, that means the corresponding input for the function must be 2 because f of 2 is 3. I know that because if you just plug in 2, you get 3. So here, to go about finding that derivative of the inverse, the derivative of the function at the input for it, which is 2, would then be just evaluating 3x squared, evaluating where x is 2, and that's 12. So then, the derivative of the inverse function, where x is 3, has to equal the reciprocal of the derivative of the function at its corresponding input, which is 2, so that's 1/12. So that's got to be the answer. Now we can check if you want to. We can check it because we can just go use the swap and solve technique. What we do is we replace the f of x with y, we swap the x and the y, and then we solve for y and replace the y with the inverse function. So then that is the inverse function of f. We can then easily find that thing's derivative just by doing normal rules. That's the derivative of the inverse. And we can then just evaluate that at our input of 3. By doing so, you get 1 over 3 times 8 to the 2/3 power. 8 to the 2/3 power is just 4. 3 times 4 is 12. So the derivative of the inverse at 3 is 1/12. Notice either way, we get the same answer. So why do it the first way? Isn't it easier just to do it the second? Just swap the variables and solve. Well, because almost never can you do that. That's why. It's really difficult, actually, to go and swap the variables and then solve for that y. It's because the expression usually is really awful looking in y. You have only ever seen examples where it's been easy. Usually, it can't be done. Let's do another numerical example. But this time I want to emphasize that we don't actually find the inverse at any point, and yet we can still find the derivative of the inverse at a single number. That does have a consequence, though, because we are going to give it input to the inverse. What we need to know is the corresponding input for the function. Because if f of a equals b, then f inverse of b is a. That means that the input of f is a. The input of f inverse will be b. Once we have that, we can then use the derivative rule for inverses, because the derivative of the inverse function at b is equal to the reciprocal of the derivative of the function f at the corresponding input a. So, for the function f of x equals 1 over x plus 1, I'd like to know the value of the derivative of the inverse at 5/4. Thing is, I don't know what the other number is, so I have to find it. But I don't want to find the inverse to get the answer. So, there's a way around it. I know that f inverse of 5/4 has to be some number. We'll just call it a. That means 5/4 must be equal to f of a. But I know what f of x equals, so I can evaluate that. That will then give me an equation in a that I can then solve. So a must have been 4. So this then means then f inverse of 5/4 is 4. So the input of the inverse is 5/4. The corresponding input for the function f is 4. So now that I have that, I can find the derivative of the inverse at 5/4. In the rule, I'll need to know the derivative of the function f. So there you go. I did it for you. So the derivative of the inverse at 5/4 must be the reciprocal of the derivative of the function f at 4. But the derivative of the function f at 4 is negative 1/16. So it's the reciprocal of that negative 16. That's the answer. That would have to be the derivative of the inverse at 5/4. And notice, nowhere in this process did I actually find what the inverse was.